We have established the tenets of quantum mechanics. Now, we are going to slowly get into systems in which quantum mechanics is applicable, and we will see how we can build a description of these systems. The first system that we are going to talk about is a particle that is as free as this colorful little bird here. We call it a free particle. What is the meaning of a free particle? We will come to that. But before we do, let us remind ourselves that so far we have discussed Schrodinger equation. We have said that Schrodinger equation yields wave functions, and these wave functions, sorry about the mistake in spelling here, these wave functions are interpreted by Max Born to be associated with what we call probability waves. So, mod psi square is equal to the probability density. That is what we have said. So far we know that psi has to be a solution of Schrodinger equation. It must be normalizable. Why? Because if psi star is probability density, then we remember that psi star, or the way it is conventionally written, psi star psi d tau is the probability of finding the particle in a small volume element d tau at a particular position. So, if it is Cartesian coordinate, d tau will be dx dy dz. So, probability of finding a particle somewhere in space, say at this point, is given by the probability of finding it in this small little box here, which is called the volume element, and we are saying the volume of this volume element is d tau. This is probability, and psi star psi is probability density. Naturally, you have to find the particle somewhere in space. So, we write integral psi star psi d tau over all space. I will just write all space here. I think in the last class I had written minus infinity to plus infinity. I will not do that, because you will see what infinity might mean here. It is not necessarily infinity. So, integrated over all space, that has to be equal to 1. That is your normalization condition. Next we said psi has to be continuous, and we will see how this is very useful in our discussion, maybe not in this module, in the next module. Now, d psi dq, this has to be continuous in Q. We are going to see that this is not a very rigid condition. This does not really arise out of Born interpretation, it arises out of the requirement that we are writing a second derivative. That is why. Psi must be single valued. This of course comes from Born interpretation. You cannot have more than one probability density for a given point, and it has to be quadratically integrable. That these are in a nutshell the conditions that a wave functions must satisfy, and as we are going to see in the next couple of modules, quantization arises out of application of these conditions, imposition of these conditions, and we will do that and we will study these 3 systems. Today we will talk about free particle, then we are going to encage that particle, put it in what is called a square wave potential, that is called the particle in a box problem, and finally we will go on to discuss hydrogen atom. But before that, I want to talk a little bit about eigenfunctions, eigenvalues and expectation values, and I have been a little lazy, that is why I have not really written these things here. I will write it in real time. So, as we said, the postulates of quantum mechanics tell us that for every observable we should be able to construct an operator. Here I am writing A, and when this operator operates on the wave function psi, we get an eigenvalue equation where the same psi is multiplied by a number. That number is called the eigenvalue. It is not necessary that always a system will be described by a wave function that is an eigenfunction of the operator that we desire, and that is what we will need to understand. You might remember that in the postulates we had said that the wave function has to be a sum of mutually orthogonal eigenfunctions. So, let us say that I have a wave function psi for some system, and we are actually going to encounter a system like this very soon, which is a linear combination of say A1 phi 1. Remember, I do not necessarily have to write psi for wave function, I can write anything. So, A1 phi 1 plus A2 phi 2 plus A3 phi 3, and these phi's are such that they are eigenfunctions. So, let us say A hat operates on the wave function phi 1 to give us I have written A already. So, let us say C1 phi 1, let us say A hat operates on phi 2 to give us C2 phi 2, and A3 A hat operates on phi 3 to give us C3 phi 3. Is psi an eigenfunction of A in that case? Let us see. Remember, these are all linear operators. So, when A hat operates on psi, what do I get? I get A1 C1 phi 1 plus A2 C2 phi 2. Where is the C1 phi 1 C2 phi 2 coming from? From here, plus A3 C3 phi 3. Now see, is there any way in which I can take this A1 phi 1 plus A2 phi 2 plus A3 phi 3 out? This will happen only if C1 equal to C2 equal to C3, is not it? If C1 equal to C2 equal to C3 equal to some C, then only then and then only I am going to get A hat psi is equal to, now C will come out and inside you get A1 phi 1 plus A2 phi 2 plus A3 phi 3, which is essentially psi. So, now I get C multiplied by psi. So, the problem now is that that is the only condition in which it will be an eigenvalue equation. So, a linear sum of eigenfunctions is an eigenfunction if the constituent eigenfunctions phi 1, phi 2, phi 3 here have the same eigenvalue. This is something that we are going to use when we talk about p orbitals later on, but this is a very specific case. What is the general case? The general case is that this is not an eigenfunction. If C1, C2 and C3 are not equal to each other, then what happens? Then what are the values that I will get if I perform some experiment? Remember, we had talked about wave function collapse. We had said that the system before measurement exists in an entangled state. When you perform a measurement, it collapses into a particular wave function depending on the experiment you perform, and that is what you see. So, when we perform an experiment on the system, I am going to see either phi 1 or phi 2 or phi 3. For a given experiment, or rather let me say for a given observation, the system is going to reveal itself to us either as phi 1 or phi 2 or phi 3, alright. And one thing I forgot to say is that phi 1, phi 2, phi 3 let us say these are all normalized wave functions. So, you are going to see either phi 1 or phi 2 or phi 3. So, the variable A that you measure, you are going to, for some experiments you are going to see a value of A1, for some experiments for some experiments you are going to see a value of C1. For some experiments you are going to get a value of C2, for some you are going to see a value of C3. Okay. What is the average value that you will get? As we said, you are going to see either C1 or C2 or C3 when you perform a particular observation or particular experiment. What is the average value that you will see? average value of let us say C, or I could have written A hat also, that is going to be, actually I am using a bad convention, I should have written C as coefficient and A as eigenvalue, but well, it is fine. So, that is going to be integral, and I hope you remember this Dirac notation, A1 phi 1 plus A2 phi 2 plus A3 phi 3, then A hat operating on this second vertical line is absolutely not necessary, it is just written so that it looks a little better. A1 phi 1 plus A2 phi 2 plus A3 phi 3. What will I do? First of all, I will work with the ket vector. I will leave the bra vector as it is. I will write A1 phi 1 plus A2 phi 2 plus A3 phi 3. And now what happens when A hat operates on phi 1? I get C1 and A1 is already there. So, in the ket vector I get A1 C1 phi 1 plus A2 C2 phi 2 plus A3 C3 phi 3. I hope you understand what I am doing. When A hat operates on phi 1, I get C1 phi 1. So, when A hat operates on A1 phi 1, I get A1 multiplied by A hat phi 1, that is equal to A1 multiplied by C1 phi 1. These are linear operators, remember, phi 1, and similarly we can proceed with phi 2 and phi 3 also. Now I will open the bracket and write what I get. This is what I get, integral A1 square will come out, C1, achha, I have missed something though, in the denominator I will get something. Denominator is also there, I am not writing it in the first line, second line at least I should write. In the denominator I get integral A1 phi 1 plus A2 phi 2 plus A3 phi 3 multiplied by A1 phi 1 plus A2 phi 2 plus A3 phi 3. Because you know there is no guarantee that this psi is normalized. So, in order to normalize it I have to divide it by this integral psi star psi also. Alright. So, let us go ahead and open this now. What will I get in the numerator? First term phi 1, so remember this phi 1 star and this is phi 1. So, I get well something like this A1 star A1, because the coefficients can also be imaginary, multiplied by C1 integral phi 1 star phi 1, that is the first term I get. Similarly, second term I get will be from say phi 2 and phi 2. Let us just take the phi I terms first. What will I get there? A2 star A2 C2 integral phi 2 star phi 2 over all space plus A3 star A3 C3 integral phi 3 star phi 3 over all space, and then I just write one more term and not write anything else, because what will be this one for example. If I take A1 phi 1 and A2 phi 2, then I will get A1 star, remember anything in bra vector is actually complex conjugate, A1 star A2, then I will get C2 is a constant, it comes out integral phi 1 phi 2 over all space, and I will get many more terms like this. The problem is integral of phi 1 phi 2 over all space is actually 0. Why? Because they are the wave functions that we said, we have defined that phi 1 phi 2 phi 3 are mutually orthogonal. So, the only terms that will survive are the ones on the top. What about the denominator? Sorry, the 3 terms that I have written out, this is going to be 0. What is the denominator? Denominator is going to be A1 star A1 This time I will just get phi 1 star phi 1 plus A2 star A2 integral phi 2 star phi 2 plus A3 star A3, I have written A square, should better correct it. Integral phi 3 star phi 3. Now see, these phi 1, phi 2, phi 3, they are all normalized, right. So, I can write like this. Now, I can just write I can be 1 or 2 or 3. Integral phi I over all space is actually equal to 1 as they are all normalized. So, what does the average value turn out to be? It turns out to be A1 star A1 C1 plus A2 star A2 C2 plus A3 star A3 C3 divided by A1 star A1 plus A2 star A2 plus A3 star A3, alright. This is your average value. So, it is important to understand what we have just seen. This is a very important aspect of quantum mechanics. What we have learned is that when you perform a particular experiment, you are going to experience one of these eigen functions. So, you will get one of their eigenvalues, fine. And then you are going to when you perform an average measurement, what will be the number of times you observe C1 or C2 or C3, that depends on AI star AI. So, mod square of the coefficient of the these wave functions gives you the fraction of times you are going to see a particular eigen value, alright. This is an important thing in quantum mechanics that we needed to know before we can go ahead further. And we have also learned in the process that if all the eigenvalues are the same, then the linear combination is going to be an eigenfunction as well, alright. That being said, let us now go ahead and talk about our free particle. The meaning of free particle is that if you write the Schrodinger equation, this V of x is going to be 0. Free particle means we have created a situation where the particle is not under any field of anything in the universe. So, you can think it is like you have an atom and you have provided ionization energy to the electron. So, the electron has just come out of the potential of the atom, or you can think of a satellite that has just come out of the gravitational potential of earth. That kind of a particle is a free particle. In fact, you can create free electrons and stuff in equipment like what are called synchrotrons. Okay. So, V of x is going to be equal to 0. So, the Schrodinger equation then for free particle boils down to this minus h cross square by 2m multiplied by d2 dx2 psi of x. Now, we are working in one dimension to start with. If we are working in 3 dimensions, if we said the particle is free in all directions, then I just have to add d2 dy2 and d2 dz2, and psi would have been a function of x and y and z, right, not very difficult to extrapolate from here. So, this is Schrodinger equation for a free particle in one dimensional space, and this here minus h cross square by 2m d2 dx2, this is the kinetic energy operator. It is often called the T operator, and here since it is along x direction, I will write T hat of x, T hat x. This is the kinetic energy operator. So, this E of course is going to be only kinetic energy for a free particle. As we said, there is no potential energy anyway. Okay. Now, this is a differential equation, and we are familiar with these differential equations, I hope. So, the trial solution that we can think of is psi of x equal to a sin kx plus b cos kx. We can think of another kind of trial function as solution as well, we will come to that. Now, here is this a good trial solution? Well, to know that, all we have to do is differentiate once, this is what you get, differentiate twice, this is what you get. I am not going through the steps because it is very simple. This is the solution. I encourage you to just do it once yourself, and then you will be convinced. Now the question I want to ask is, what is this k? I have got d2 dx2 of psi of x equal to minus k square psi x. What is k then? If I plug k back into the original Schrodinger equation, we see that if I replace d2 dx2 psi of x by minus k square psi of x, then I get h cross by 2m from here, k square psi of x from here, that is equal to E multiplied by psi of x. Or in other words, I can write this energy as h cross square k square by 2m. K is a measure of energy, or rather K is a measure of energy, and remember that this energy is entirely kinetic energy. So I can write another expression here. I know that if it is kinetic energy, then what is the relationship between kinetic energy and say linear momentum? I will write Px here because the motion is only along x. So E is equal to Px square by 2m, we know that. So if I compare this expression and this expression, then what will I get? 2m in the denominator. So Px square turns out to be h cross square k square, and so well, what is Px then? That will be equal to plus minus k h cross. So what we see is that it appears that we are going to have a momentum of k h cross, and the particle can move in this direction or in that direction. Okay. So that is what seems to come out, and we are going to arrive at it in another way also. So k then is equal to root 2me divided by h cross, but do not forget the plus minus sign. Okay. Plug it back into the trial solution, you get an expression for psi of x as a sine root over 2me by h cross into x plus b cos root over 2me by h cross into x. And if I plot it, this is the kind of function that I get. This looks like a cos function or a sine function, it is not. I actually multiplied sine x by some 3 or something and added it to cos x by 2 or something. So this is what you get. Now is this a good wave function? Actually it is not, because you can see clearly that it goes from plus infinity to minus infinity, it does not become 0 anywhere, it is not normalizable. So there is a little bit of a problem. So to work with a free particle, what one does is one uses the technique of box normalization, which means that you say that you set some limits, you set long limits, say 10 angstrom, 15 angstrom, 20 angstrom, something like that, and you say that the particle exists within this limit and you normalize within that. Of course, it is not a very rigid way of doing it, but that is the best you can do. So be aware that the wave function for free particle is not really a perfect wave function. Alright. That being said, we can actually write the wave function in a different manner also. Instead of writing the sine and cosine functions, I can write this kind of an exponential function, e to the power ikx plus d e to the power minus ikx. I leave it to you to differentiate it twice and convince yourself that this function also satisfies the Schrodinger equation for a free particle. You can arrive at it in another way. I think we all know that e to the power ikx is equal to cos kx plus I sin kx. E to the power minus ikx is equal to cos kx minus I sin kx. Now if you multiply e to the power ikx plus by c, multiply e to the power minus ikx by d, add them up, you are going to get something that will be a sum of a sine and cosine functions, alright. But the reason, the good thing about writing the function in this particular form is that it starts making sense. Why does it start making sense? Well, the momentum operator, what is momentum operator? I will come to that. Before that, let me just say this. I differentiate e to the power ikx, let us say, with respect to x. What do I get? I get ik multiplied by e to the power ikx. So this is actually an eigenvalue equation. The only problem is that the eigenvalue is imaginary. But it is not really a problem, because if you think of the linear momentum operator is actually h cross by I multiplied by d dx. So you multiply the previous result ik e to the power ikx by h cross by I, you end up getting h cross k. What is h cross k? H cross k then is the value of the linear momentum that you get if the linear momentum operates on the first term in the wave function. What would you get if the linear momentum operates on the second term of the wave function? You are going to get minus h cross k. This is absolutely in line with the argument that we had proposed a little while ago, is not it? We had also obtained the values of plus h cross k and minus h cross k for the momentum even before using the operator. So, using the operator it makes sense. That is point number 1. So, we see that the particle can move in this direction or in that direction. What is the probability? Probability is equal, there is no bias for any direction, and probability being equal is given well ensures that the coefficients also have to be such that their mod squares have to be same. Okay. This discussion that we just performed, I hope it rings a bell about the discussion that we performed maybe 5-10 minutes ago writing on the surface. Remember what happened? We perform a measurement, we are going to experience one of the eigenfunctions of that particular operator. That is what we see here. So, linear momentum can be either plus h cross k or minus h cross k, right, that is what we learned. Average value of course has to be equal to 0. Again I leave it to you to plug in this wave function into the expression for average value. Of course, you will have to use this second form and you can work it out yourself, but even without doing it we can see from simple logic that probability of moving in either direction should be the same. So, this average value must be equal to 0. Average value of momentum is equal to 0, average value of energy is not equal to 0 because energy depends on k square and not k. Okay. So, what have we got so far? Is there any restriction of k? No. So, there is no restriction of E as well. So, for a free particle, the first quantum mechanical system we have studied, there is no quantization. Where will quantization arise from? If we confine the particle, if we put it in a box, we will see in the next part, in the next class that quantization arises nicely.